So how far did we get with those polar coordinates? Okay. 2a, did we do 2a?
2a, yes.
More or less. So we ran out of time, but basically I rushed through this and I sort of finished it, or almost finished it. So we are just rewriting the integral. We are not really computing them at this moment. We can calculate some integrals in polar coordinates in exercise 3, a and b. So C, we might leave C, we might run out of time because we have 1, 2, 3, 4, 5, 6, 7. Yeah, next time.
Did you finish at 2a?
I think we did, didn't we?
Yeah, we did.
I think we did. In 2a we had 2 concentric circles. In 2a, so I'm going back to 2a very quickly. 2 concentric circles like this. Radius 1, r is 1, and r is 3. And then we had 2 straight lines. Oh no, I think we did exercise 1.
Yeah, we only did.
Only exercise 1. With those, right, now I remember. So, alright, so exercise 2a is the first one we should do now. Then, so obviously we can see that x squared plus y squared equals 1 is actually the circle, and in polar coordinates it can be written simply.
We have done also 2a. We did 1 and 2a. Yes.
Really?
Yes.
I
And
think
1.
we did 1.
And 1 also.
We did. So why are some people complaining that we haven't done 2a?
No, we didn't do 2a.
Yeah, we did. 2a. Okay, so what we actually had in 2a, there was one line that corresponded to the angle 30 degrees pi over 6, because the equation of this was y equals 1 over root 3 times x. That was the square root of 3 times y greater than or equal to x. So with this one, we probably did it not last time, but the time before, the last week. That's more possible, probably, because last time we just did exercises. It could be, right. So I'm just reminding you very quickly y equals square root of 3x, 2 lines, which means they correspond to angles pi over 6 and pi over 3, because if you remember, the gradient of a line is the tangent of the angle of this line between this line and the x-axis. And therefore we have pi over 6 this angle, pi over 3 this angle, so the region of integration is that. And we did. So if you say we did, then maybe we did. I don't remember.
No, we didn't. No, we didn't.
Maybe I did myself. Maybe I did myself. I don't know.
People, choose. Either we did it or we did not.
No, we did not. Let's do it now.
Some people were mumbling. Okay. All right. So what we had here, the first circle, x squared plus y squared equals 1, which corresponds to the equation radius equals 1. And x squared plus y squared equals 9, which means the radius of the circle is 3, so that's this other circle. R equals 3, R equals 1. And so we can just write from 1 to 3. And for the angles for d5, we have to think what we might be doing there. So in exercise 2, I'm reminding you, we only have to write this integral in the polar form, but we cannot calculate it because we simply do not know the function. So we have some abstract function. Okay, we can write the function of r and phi I'm reminding you about this extra r in the polar coordinates. This extra r happens only when we have to transform the integral from Cartesian to polar form, because if you have an integral in the polar form, obviously it's already counted in and it's already involved. So only when we transform, we put this extra r. Last week's papers, nothing new. And the angles, so if we have a straight line, y equals square root of 3x. Remember that the square root of 3 is the tangent, the gradient of a line is the tangent of the angle this line forms with the x-axis. So that's a very useful thing for us, because I know that square root of 3 is the tangent of 60 degrees, pi over 3. So that's how I know that the equation of this line, as it is passing through the center coordinates, through the origin, which can also be used as the pole, is phi equals pi over 3. Similarly, the equation of this line originally was square root of 3y equals x. Well, there was an inequality, but to see the line itself, we need the equation. So I divide both sides by square root of 3, and I see this number, which is the tangent of the 30-degree angle. So that's why this line can be written phi equals pi over 6. Well, actually, they are half lines. And so now I can see that I have to integrate whatever function is there, r dr. R goes from value 1 to value 3 for all the angles between these two. So we integrate by d phi from pi over 6 to pi over 3. So this is actually a pretty simple, a pretty straightforward integral. Obviously, these kinds of integral might arise in whatever areas where we encounter circles, perhaps in some engineering or perhaps in some other problems in applied physics, for example, also possible. But it's a pretty basic integral and useful to know. At least useful to understand how the equations of line are transformed into the polar form. Understanding how the equation of a circle is transformed into the polar form, and seeing that the integral really becomes simpler. Well, it depends on the function. It might not become simpler. If this function is really ugly, then it might not become simpler. But at least the boundaries of integration do become simpler. That was 2a. Now 2b, and I'm not erasing 2a yet. 2b. We have the domain, the region of integration x squared plus y squared is less than or equal to a squared, and x plus y greater than or equal to a. So we should probably make a sketch. We will need that anyway. We should transform these into polar coordinates. So this is obviously the inside of a circle. The inside of a circle with radius a. The center of the coordinates is there. I also should remind you that about the general equation of a circle, which went like this. I think last time some people were surprised at this equation. It's an equation of a circle with radius r and the center at x0, y0. Sometimes we need to use this form when we have to transform something. In this case, it's the simple one. So the radius is a. We are assuming, of course, that a is a positive constant, because if a is negative, then nothing actually changes. It will be the same. So it will be inside this circle, x plus y greater than or equal to I. So we are using an equation y equals a minus x. That's a straight line. If x equals 0, then y is a, so it's this point. If x is a, then y is 0, it's this point. So the line is this. Y equals a minus x, this line. So the region of integration is this. So what can we tell about this immediately? We can see that the angle goes from 0 to 90 degrees or pi over 2. So that's something we can already write down, no problem. We can see already what's going on. Now, of course, we will have the function r, phi, r, dr. We don't know what's in there. We don't know. We are not told the function. Now, what about the boundaries of this integration for r? Obviously, we're going from the line to the circle. So the upper boundary has to be a. We are using all radius values from this to a, from this to a, as we go along a radius. So from the line, from the point on the line to the point on the circle. The point on the circle has the property r equals a, so the upper boundary is a for all these points. The upper value of r is always the same. Now we should obviously transform the equation of that line into polar coordinates. So what we can do is, okay, I'm taking this, so it's r sine phi plus, no, this is cosine. The first one is cosine. Don't want to confuse you. It doesn't matter. The order doesn't matter, but still, x is r cosine phi, y is r sine phi. And if the equation is like this, then I can express r as a divided by sine phi plus cosine phi. So this is the lower boundary. So this is a divided by sine phi plus cosine phi. Like this. So what we have to do now is just integrate if we know the function. If we don't know the function, we have the answer. This is the answer. So whatever the equation of a line in Cartesian coordinates is, you can always transform this equation in the polar form. The question is, of course, how simple and efficient it's going to be. But in principle, if you have the equation of a line or a curve in polar coordinates, in Cartesian coordinates, in xy form, you can always transform them into r phi form. Just put r sine phi instead of y everywhere, and r cosine phi instead of x everywhere. And then, of course, simplify whatever you can, using perhaps the properties, a little bit of properties of trigonometric functions, and so on and so on. So this was not so bad. 2c. 2c. Y equals x, y equals minus x, y equals 1. So y equals x, it's this line. Y equals minus x, it's this line. So y equals x, y equals minus x. And, also, y equals 1. So y equals 1, this line. So obviously the region of integration is this, which, well, obviously it's not so very nice in polar coordinates. It seems that this region of integration would be preferable in the Cartesian coordinates. Nice and clean. But it sometimes happens that the function to be integrated works better in polar coordinates. And then, obviously, we leave the Cartesian and move on, transform them to the polar coordinates. So you see there are two factors involved. One factor involved is the boundaries. So whether they look nicer and are easier to deal with in polar form or in Cartesian form. And the second factor influencing this thing is the function itself. Ideally, we move to polar coordinates when both the boundaries and the function are better off in polar coordinates. If one of them is better in polar coordinates and the other one is better in the Cartesian coordinates, then it's 50-50. Alright, so what can we say about this integral? Is there something obvious? I would say the angles are obvious. 45 degrees. So actually the integration by phi, the second integration, would be from 45 degrees, which is pi over 4, to 3 pi over 4. Because this angle is obviously 45 degrees, as we are talking about the bisector of the first and the second quadrant, the two bisectors, or the diagonals of squares. Now, how to do this line in polar coordinates? What we have to write is r sine phi equals 1, so r equals 1 over sine phi. So the lower boundary is what? 0, because this corresponds, if you remember yesterday, two days ago, I showed you those 4 basic types of polar regions of integration. And this was the situation where we have a point coinciding with the pole, and then we have 2 tangents at the same point, and then we can see the angles. And we were considering these angles. So what we have to do is from pi over 4 to 3 pi over 4, but the radius, the r value changes from 0 to this line. So from 0 to this. This is this. So it's 1 over sine phi. So the integral would look like this. So in most cases, you have to be able to transform the equation of a straight line into the polar form, and the equation of a circle into the polar form. And the equation of the circle could be like this. It could be like this. But again, if you just replace all x's by r cosine phi and y's by r sine phi, then basically you can deal with that as well. So you will get still something fairly simple. As you remember, we had something like 2 sine phi minus 4 cosine phi or something like that. We did it last time and previously. D, my favorite curve, well, not exactly a function. So the lemniscate of Bernoulli looks like an infinity sign. A very interesting curve. So you are given the Cartesian equation of this lemniscate of Bernoulli. X squared plus y squared, all of it squared, equals a squared, where a is some constant, x squared minus y squared. Just like this. So the region of integration is obviously inside both leaves or petals, whatever. So that's the region of integration. And we need to discover what is the equation of this curve in polar coordinates, and obviously we need to discover the angles. So 2 things that are important to us. Okay, let's start working. So this is r squared, obviously, the distance from the center, x squared plus y squared, and squared again, right? A squared, constant. This r squared cosine squared phi minus r squared sine cosine squared phi. So now we can divide both sides by r squared. So this is r to the 4 divided by r squared, we get simply r squared. On this side we have a squared times cosine square phi minus sine square phi. This is a very good trig formula. A very nice one.
Sine to phi.
It's the cosine of 2 phi, yes, cosine of the double angle, so it's a squared, cosine of the double angle. Yes, right. So you see the equation of the curve in polar form is very nice, very simple. Now, just to decide what to do. Just to decide what to do. So first of all, we have r squared, not r itself. We have a squared and we have cosine of 2 phi. R squared must be positive or at worst 0. A squared, a square of some constant, it's also positive or at worst 0. So what does it tell us about cosine 2 phi?
It should be positive.
Should be positive or again at worst 0. So what we see from this, the cosine of 2 phi must be greater than or equal to 0. I'm not writing less than or equal to 1 because that's obvious. Because this side, the left-hand side, is positive, so to make the right-hand side positive too, it must be positive, otherwise we can't find the r value at all. So cosine of 2 phi must be greater than or equal to 0. This is the reason why you studied some trigonometric equations at school. Well, one of the reasons, obviously. So the trigonometric circle. So if I want 2 phi, the cosine of 2 phi to be positive, then 2 phi must be somewhere on the right half plane. So actually I can write that 2 phi is greater than or equal to minus pi half, less than or equal to pi half. Well, basically, of course, if I move one circle on, one full revolution on, I get the same thing. So basically, it's not just that. It could be some other values as well. For now, I'm not trying to squeeze anything in there, but we see the pi limitations from minus pi over 4 to plus pi over 4. So now we see the angles. Now we see the angles. This function makes sense only if phi is between minus 45 degrees and plus 45 degrees. For any value of a, for any positive constant a, so pi over 4 minus pi over 4. And then of course for the left-hand part also the corresponding values. This would be 3 pi over 4. And this would be 5 pi over 4, simply to deal with the corresponding angles. So that for the sake of calculus, for the sake of understanding and practical calculations, I was not trying to make this very complicated, but obviously this is the first part and this is the second part where the cosine of 2 phi values will be again. So we already have the boundaries, these boundaries and then these boundaries for the outer integral, for the integration by 5. Which part can I erase? Can I erase this?
The A part.
Yeah, the first one. No, here.
Then I will jump back and forth. Okay, I can't. Okay, some people are slow to copy. Now, the second thing to do is to define R. So the R value, obviously from there, will be A times the square root of cosine 2 phi. A square root of cosine 2 phi. Assuming, obviously, that A is positive, we are assuming that A is positive. Otherwise, it makes not much sense. So, by the way, in that graph, in the picture, what do you think corresponds to the constant A? What do you think the constant A, the number A means? What does the constant A mean in that graph? Can you figure it out from the Cartesian equation or from this equation? Can I see the constant A somewhere in the graph?
Yes.
Where?
So perhaps it is. So intersection with the x.
Yes. This is A, and this is obviously minus A. The furthest point left. We are assuming that A is a positive number. If A is negative, then, well, what's the difference? A here minus A there. So we are assuming that A is positive. Anyway, we can see that for that right part, from minus pi over 4 to plus pi over 4, by d phi, we have to integrate the r integral, r phi r dr, from 0 to this a square root of cosine 2 phi. And then we have to do this once again, but for the boundaries from, for example, 3 pi over 4 to 5 pi over 4, so that we cover this part. So plus 3 pi over 4, 5 pi over 4, d phi, 0 a cosine 2 phi, f r phi r dr. A lot of this is simply mechanically writing. Function r dr.
But the answers is different.
Yes, I know. Right now, I realize that very possibly I had forgotten something or missed something. Yes, I know. I didn't get the boundaries right. Now, as I was writing it on the board, I realized that I had not done it correctly. So I'm not sending those answers to everybody yet before I correct. E. 2E. X squared plus y squared equals 8. So that means r squared is 8 and r is 2 square roots of 2. And the second circle, x squared plus y squared equals 4x. So now, in this case, we have to transform it into this form. It must be a circle. Whenever we see x squared plus y squared, and then perhaps some simple linear x and y terms, whenever we say that, it must be a circle. If we have x squared plus y squared and then linear terms, it must be a circle. If x squared and y squared have different positive coefficients, then it would be an ellipse, but we are not dealing with those. Let's leave that for the architects. So x squared minus 4x, so I need plus 4 to complete the square. Remember that we need a perfect square, so I bring 4x to the left hand side, and obviously to be able to complete the square I need to add 4y squared. So on the right, this moved over, but we added 4, so we have to add 4 on the right as well. So this is again the same pattern that we saw last time, and I think in the lecture last Thursday, because I demonstrated this circle. I have shown obtaining those circles several times now. This is the third time, I believe. I think.
Yes.
Is 2 squared. So this means that the center of this circle is at the point 2, 0, which means it's on the x-axis. This means that the radius is 2. And when transforming this into polar coordinates, we see r squared equals 4r cosine phi, or r is 4 cosine phi. So whenever you see a circle in Cartesian coordinates, you should remember that it will transform into something like this, or something number times sine phi if the center is on the y-axis. And sometimes it might transform into a linear combination of these two. 4 cosine phi minus 6 sine phi, that would mean that the center is at 3 minus 2, because we see that this 4 arises from doubling 2. It's 4 here because it's 2 times 2. So obviously a circle passing through the origin, a circle having the center on one of the axes. So in this case, the sketch would be, so I'm starting with this one. So the center is at the point, okay, this will be 2, the radius is 2, so it passes through the origin or the pole. So we have this circle, and the equation of this circle is polar form. In polar form, this equation is r equals 2. That's the more complicated circle. The other circle, the first circle, is simple. The center is at the origin of the pole. The radius is 2 square root of 2, though, but we can actually see, we can find an intersection point. For instance, well, it's quite possible to guess. If x and y values are equal, they have to be 2. If x is 2 and y is 2, x2, y2, it's a point on this circle. x2, y2, because the radius is 2. This point belongs to the first circle. That point actually lies on the first circle. It's important that we see the intersection points because we need to decide what the angles are. We need to understand those angles. That's another circle. And so when we look at the conditions in the task, greater than the first circle, so outside the first circle, but inside the second circle, the radius, so the distance has to be greater than 2 square root of 2, so outside the first circle, but less than 4x, and if we move it over to the left-hand side, so less than this, so it's this part. The only question now is, of course, figuring out the angles. I would think they are
45 degrees.
easy enough. 45 degrees, obviously, because 2, 2. It's an important point there.
Minus 45.
Yes, so from minus pi over 4 to pi over 4, please use radians. Because if you use numbers like 45, the value of the integral is going to change. Use the correct numbers. So in calculus, we don't do degrees really. If we are dealing with trigonometric functions, then x is always, well, the angle is always considered in radians and not in degrees. Degrees are kept for geometry. For calculus, we are using radians always. That goes without saying, but I have seen people using degrees and getting wrong results. And so the function it's boring. You always have to write it and write it and write it, just like lim. I remember you hated writing limits because lim, useless. Well, not really useless, but still. So from this circle, so that would be from the value 2 square root of 2 to this value, to the outer circle, not the outer circle, 4 cosine phi. And now, of course, it depends on how unpleasant this function is, because obviously when we have integrated it, we will have to put cosine phi instead of r, which might make the function very, very unpleasant or not. So again, it's quite obvious that the simplest integrals would be easy to do, and then there are some other integrals that are not so easy anymore. That was 2e. So we still have to do 3a and b.
And 2f.
So now it says find the following integrals. Now we have to integrate.
What about 2f?
Finally.
What about 2f?
Oh, I forgot 2f. Oh, all right, 2f. Right. Thank you. I did not decide to ignore it. I simply forgot. So f. X squared plus y squared equals ax. Can you guess what it would look like? And x squared plus y squared equals 2ax. That's the second one. So looking at the previous one, can you guess something at least? At least guess something. The polar equation, if you compare this and what we did and how we got
Center will
this,
be on the square root of a and
A
0.
divided by 2.
a half is the coordinate of the center and the radius will be also the same, a half. But the equation will have a itself. So the equation in polar form will be r equals a cosine phi. And for this, the equation will be a r equals 2a cosine phi. Then obviously we remember that we got 2 dividing this number 4 by 2, so it's half of a. So the center will be at a half. Obviously, so the center will be at the point a half, 0 on the x-axis. The radius of this, I'm writing the capital R because this is simply the coordinate r, but this is the radius of a circle. The radius will also be a half, and obviously will pass through the origin. And for this one, half of this, so therefore the x-coordinate of the center is a, in a similar manner, 0, and the radius is a as well. So this is actually a good example, this is a good exercise because it shows you the pattern we use, and well, some people might remember this type of thing. If we have something like this, then we have this. So what happens when we have 2ax plus 2by? Then the center will be at the point AB, obviously, and the radius will be, or whatever happens there. Okay, sketch. So, this will be more decent. Alright, so this is a half. This is the point A, obviously. This is the first circle. Radius is a half. The center is at a half on the x-axis. By the way, talking about x-axis, I am using the Cartesian coordinates x and y, and I'm not actually sketching, I'm not writing down the polar coordinates in the form pole P and the polar axis, whatever. So my basic system in the sketch is still Cartesian, but I try to switch my thinking over to the polar coordinates. What we see visually, we see still the Cartesian axis of coordinates, but we think in terms of polar system. And the second circle, okay, the center is here, the radiuses are, so it's something like this. And this will be the point 2A. It should look like this. 2 circles. Now, let's analyze further. Square root of 3y equals x. Square root of 3y equals x means y equals 1 over square root of 3x. 1 over root 3 is the tangent of 30 degrees, which means that this line is simply phi equals pi over 6. Okay, 30 degrees, that would be this one. And the second line is y equals x. If y equals x, then the angle for this line is pi over 4. This. So phi equals pi over 4. And the region of integration, obviously this. So for the line y equals x, the polar definition or the polar equation simply requires the angle because it's passing through the center and all the points on this line, or rather on the half line, correspond to the condition phi. The angle is this. For all the possible values of r, doesn't matter what the r value is, phi is pi over 6. So this kind of line, the line that passes through the origin, is very easy to transform into the polar form. If the line does not pass through the origin, we already had a horizontal line, but we also had one slant line. So we have seen that it's all possible. It's not so bad. So now finally my integral finished. In the finished form would be from pi over 6 to pi over 4 d phi integral from this, where? From this, the inner circle, that boundary would be described by this expression a cosine phi, to this that has the equation 2a cosine phi. So I should write. So the problem is that I didn't write it in the sketch, in the diagram. I wrote the equations on the lines. I didn't write the equations on the circles, and that can be confusing sometimes. So my advice is as soon as you sketch the curve and find the polar equation, write down the polar equation in that sketch immediately. It will help you to write this part, because otherwise you have to look, where can I find the boundaries? If you write them down in the sketch, you can find them immediately, hopefully. All right, I didn't finish. Now, questions about these? No questions, all right. Then we just have time for 3A and B, and 3C can be left to have some fun. Or for you to have some fun. Something more. Three. 3A. Okay. Double integral sine square root x squared plus y squared dx dy, where d is bounded by x squared plus y squared equals pi squared and x squared plus y squared equals 4 pi squared. And that's all. So obviously this is a circle, this is a larger circle. So what we see is that the region of integration is a ring. It's a ring. The inner ring will be radius pi, the outer ring will be with radius 2 pi. So, okay, one, the other. So this is r is pi, this is r is 2 pi. And the region of integration is this because there are no other limitations, no other constraints, just this. Yes, I had a good reason why I didn't want to let too many people retake during this test, during this lecture. One doesn't teach for 30 years without gaining some experience, you know. Okay. So the integral, like this, we still need to fix this. The inner function. So first of all, obviously the angles. What about the boundaries of phi integral? It goes a full circle. There are no other constraints. So from 0 to 2 pi. From 0 to 2 pi. No other constraints. Now this integral will go the radius. The r value will go from pi to 2 pi, so pi, 2 pi, almost like a rectangle. So you can see that a ring in polar coordinates is just like a rectangle in Cartesian coordinates. It doesn't look like one. Alright, so what about this? Sine of square root of x squared plus y squared. What is this?
R.
That's r. So I have sine r. No, I have to remember that I multiply by r. So it's sine r times r dr. Now we have to integrate that by parts. By parts. Alright. I'm doing it somewhere on the side. Pi, 2 pi, r, sine r, dr. Okay, so the u function is r and du is dr and dv is sine r dr, which means the v function is the integral of this. When we integrate sine, we get minus cosine r. Okay, so we have uv, a good revision of integration, minus r cosine r, minus integral v du, so it's minus cosine r dr. All of this will be in between these two boundaries. Okay, I will write it like this, so that I don't have to write it too many times. So it's minus r cosine r, minus will make a plus, and integrating cosine we get sine, plus sine r, pi, 2 pi. Now let's see. Minus 2 pi cosine 2 pi plus sine 2 pi. Minus, now let's put this in, minus pi cosine pi plus sine pi. I'm simply putting in the boundaries, I'm not doing any calculations yet. But now, sine of 2 pi, sine of pi, what are these? What's that? That's 0. Sine of 2 pi, sine of pi. If you remember, the trigonometric circle, sine of pi, sine of 2 pi, both 0. Now the next, cosine of 2 pi.
1.
Cosine of 2 pi is 1. Yes, so now we have minus 2 pi. Minus 2 pi. And this cosine of pi is minus 1. So if I multiply pi minus pi, I get pi. So it's minus 2 pi minus pi, it's minus 3 pi. Not so bad. So now I can come back to this and write from 0 to 2 pi the integral of minus 3 pi d pi. It's a constant. So I have minus 3 pi phi dealing with this as with a constant. It is a constant actually. From 0 to 2 pi. So I have minus 6 pi squared, the answer is negative. Okay, by the way, even with that lemniscate, for example, with that infinity curve, sometimes people actually ask, but nobody asked me this time, sometimes people ask me, sorry, I know I'm talking fast. Yes. They use fast one thing. If both those parts are identical, these two parts, they are identical. Why can't I write 2 times integral on one part? The reason for that is that I didn't know what the function is. You see, if the function is also symmetrical, the function values are symmetrical in these both parts, then I can simply take the integral in one part and double it. But if the function is not symmetrical, and in that example I didn't know, because it wasn't given, if the function is not symmetrical, then the integral on this region will be different from the integral on this region. It depends on the function. The regions themselves, they are symmetrical, they are identical and they are symmetrical. The areas are the same. But if we are to integrate a function which is not the same in both parts, then the integrals of these two parts will not be the same. It depends on the function, exactly. If you see that the function is symmetrical, in other words, if you change the signs of x and y and you still get the same value, in that case you can say, yes, those integrals are identical. For example, if you can say that the function is, let's say, even, if you change both the signs, or if you change the sign of x and the function doesn't change anyway, then you can say it's an even function. Although we don't really call them even and odd with 2 variables, but still. If the function is odd, you might say that the integrals will be opposite, the values will be opposite, perhaps. But in general, we don't know that. In general, we don't know that. So you have to be careful with this. If you decide,
this should be, this is already the second part of the, here, this part. Yes.
last one for today is 3b. xy squared dx dy. And the boundaries are x squared plus y squared equals 2y and x squared plus y squared is 4y. It's very similar to what we had previously with ax, 2ax, only in this case it will go in the y direction. So in this case, okay, I will repeat it. I will repeat the idea. We need plus 1, we need plus 1. So x plus y x squared plus y minus 1 squared is 1. So the center of this will be at the point 0, 1. And the radius of this will be 1. And the equation of this will be r equals 2 sine phi. Because this is r squared equals 2r sine phi. That's how we get this. And for this one, in a similar way, we get the center 2 at 0, 2, and the radius will be 2, and the equation will be r 4 sine phi. And now we can sketch. This, yes, we already had it. Like this. So, the region of integration is this between the two circles. Obviously, the lower boundary, the upper boundary for the R integral.
But it will go up, and not right. It will go up.
Sine, right, sorry. Yes, right. I just went by inertia. Like this. Okay, what are the angles? What are the angles?
45.
0 to 3.
From, this is the tangent line, so it's from 0 to 5, right? Now, this function, alright, let's see. This will be transformed, so from 0 to pi d phi. This goes from 2 sine phi to 4 sine phi. The function goes x times cosine phi, r times cosine phi times r squared times sine squared phi, so it's r cubed, but we still need to do the r, so it's actually r to the 4th because y squared is r squared, sine squared phi, x is r cosine phi, and we still have one extra r from the differential. So the function looks like this, and now we have to integrate it.
It will be sine in the 7th grade in the end.
It will be sine to some, yes. Because for this we will have sine to the 4th, so this will be sine to the 6th, and cosine can be brought into the differential. Alright, so I am now erasing the previous one.
R to the 5th cosine phi sine.
Alright, so now I'm integrating 2 sine phi, 4 sine phi, cosine phi. Okay, well actually I'm going to do, I prefer to do what I did on Tuesday. I will take these. This is a constant with respect to r. I'm just taking them out. I don't want to involve them in that integral when I integrate. So I am now moving these out of this integral simply because they are constants for this inner integral. For this integral, they are constants. I'm taking them out. Cosine phi, sine square phi, d phi, it's just all out there. And what remains is only r to the 4th. So this makes it easier to integrate. Now I'm only integrating r to the 4th, which is of course r to the 5th over 5 from 2 sine phi to 4 sine phi. What are you hoping for? block of what? Alright, so in this, 4 to the 5th, it's the same as 2 to the 10th, 1024. 1024 sine to the 5th, 4 over 5 minus, now we put 2, so it's 32 sine to the 5th, 5 over 5 everything, so it's 9 something, 2 over 5 sine to the 5th, 5. And now I can return here and finish my original integral. So I'm taking this back. So yes, it is 0. Should be. No?
It is 0.
It should be 0.
It is.
Because it's 0, so
Yeah.
so we can just don't do it because it's from
Where
0 to
is
5.
0? Wait. Where?
It's from 0 to 5.
From 0 to pi.
So yeah,
So,
so the function is sine something and
sine, yeah, well, of course, but I still have to show. I understand that you understand that it's 0, but I have to show why it is 0 to everybody. Yes, it is. And sometimes it just happens like that. Right? So we have from 0 to pi. Now I took the constant out, sine to the 5th, sine squared. So I have sine to the 7th, phi. Now I have cosine phi, d phi. I have it like this. So remember that this actually is d of sine phi. We can use substitution or we can simply remember that d sine phi is the derivative cosine times d phi. So what I actually have is u to the 7th du. So now we have, okay, I have to write that. Now actually I can change. If phi is 0, then u, this is u, sine function is u, is 0. And if phi is pi, sine of pi is also 0. Then u is also 0. So what I actually have is this. When I change the boundaries of integration,
because it didn't separate.
when I change the boundaries of integration from phi to u simply by calculating, I see that the final answer will be 0. Without even integrating. It. It's simply because sine of 0 is 0 and sine of pi is also 0. If I had different boundaries of integration, I might get something interesting, something different. But because I had to go from 0 to pi, because I had this half circle, or actually this path between two circles going 180 degrees from 0 to pi, my final answer turns out to be 0. If I had chosen different boundaries of integration, if I had added some extra constraints, some extra angles, then we might get something else, obviously.
I think
All right.
overall the first one is the hardest.
Yeah.
Is it?
It is. It's true. I mean the calculation.
Okay.
It's too many square root of 3 square. Yeah.
Well, it's because you have to see those angles, you estimate those angles, and 3 parts. And the worst thing about these 3 parts, I think, the worst thing about those 3 parts is that this is very difficult to see. So how do we change are like this. So it's not so easy to notice that it goes from 0 to this, because this is a very small part. This is a very, very small part. Okay, looks like there's no more time for anything else. So, those who are not retaking anything today, see